Invitation. I learned about a lot of these things that I'll speak about today while I was working with Giorgio Ottaviani in Florence, Italy. That's why I put a picture of Florence from Piazzale Michelangelo. But okay, so secant varieties were mentioned in a sense in the previous talk, but let me repeat. What is a secant variety? So if you have a projective variety, x and Pn, then the x rank of a point is the number of points from that variety you need to sum up to get the point that you started with. And I'm messing around with brackets because I'm working in the affine space most of the time, but I still want to think about projective varieties. So the Zariski closure of the points of x rank R is what we'll call the secant variety. And the points inside this secant variety are called the points of x border rank R. I think Dario Bini might be responsible for this term, border rank. But taking Zariski closure causes problems, and I have an example here, which was one of the questions in the previous talk, which is, can the rank be larger? And so I have a tensor here. We'll talk about tensors in a moment, of rank 3, but border rank 2, not 2 factorial, 2. And it's the same thing. So this is what you may talk about at a cocktail party afterwards. Matrix rank is upper semi-continuous. But tensor rank is not upper semi-continuous, and this might make people really mad. So this guy is like not happy that tensor rank is not upper semi-continuous. Yeah, that might be what he's mad about too. So anyway, if you take something out of the talk about tensors, is that we call it rank, but it doesn't work exactly like you think rank might work. But okay, so here's one slide on secant varieties and tensors before I tell you maybe why I care about some of these things. So let's suppose we have 3 vector spaces, A, B, and C, and let's give them their natural basis indexed by A's, B's, and C's. Then the tensor product is just the vector space that has basis equal to the tensor product of the other basis elements. So in particular, its dimension is the product of the other dimensions. And well, that's how I like to think about the tensor product space. So the Segre variety is the set of rank 1 tensors. And if you like statistics for next week, this is called the independence model. And it's defined by the Segre embedding that takes 3 vectors, u, v, and w, and takes their outer product. Well, so in coordinates, the table Pij has entries ui times vj times wk. Okay, so that's a rank 1 tensor. The rth secant variety to the Segre variety is those points that have x rank r, where x is the Segre. And in coordinates, well, we can write a point as the sum here. This is very small, but the sum of a bunch of rank 1 terms. Okay, so we might actually want to work over the real numbers or the probability simplex or somewhere else, but today we're just going to work over complex numbers. Okay, so here are some applications, a very large page of applications of secant varieties. So why we might care to study secant varieties. So one is classical algebraic geometry. This is a seminar on algebraic geometry. So I asked a couple of people at lunch today, why is every curve embeddable in P3? And the reason is, well, if the secant variety doesn't fill the ambient space, you can project the variety down into a smaller space, okay, isomorphically. So keep doing this, and you find that secant variety of a curve is 3-dimensional. So that's where you can put a curve. Okay, so another reason why we might like secant varieties is algebraic complexity theory. And there'll be a whole semester on that at Berkeley in the fall. But the basic idea is to bound the rank of some algorithms based on ranks of tensors. And matrix multiplication, thought of as a tensor, is a good example of that one. Okay, algebraic statistics and phylogenetics. Suppose we have many species, and we'd like to infer their phylogenetic evolutionary tree. We may try to do that by understanding equations of mixture models. And this is really a secant variety question as far as I'm concerned. And in one case, for star trees, for then this question is known as the Salmon conjecture. Another place we might study it is signal processing. So if every Korean person I know has a large cell phone and they all want to talk to the cell phone tower at the same time, like on the bus, and how can you let everyone speak over the same channel and still be able to recover uniquely what everyone is saying? So this is a tensor decomposition problem, which is also related to secant varieties. And there are many others, which I've listed here. So I'd love to talk about any of those later. So those are the motivations for me for why study secant varieties. So the first questions you ask when you hear about a variety is, what's its dimension? Well, once you know the variety you're studying with X, maybe you ask, what's the dimension of its secant variety? So you know whether you're living in the best space possible. Can you project it into a smaller space? You might ask, when does the secant variety fill the ambient space? When this doesn't happen when you expect it to, you call that a defective case. Well, the next question you might ask is, what are the equations of the secant variety? How do I determine whether a point in projective space is on my secant variety or not? Okay? That goes back to answering many of these questions, algebraic complexity and so on. Determine the border rank of a given form, the X border rank. Another one which I think is very interesting, and there's been much recent progress in the last year or so, is generic identifiability. That means given a point in projective space that's random or generic, do you expect that it has a unique decomposition, ignoring change of order and rescaling, as a sum of points from the variety X? And then you might be really ambitious and ask, can I actually find the decomposition? If it's unique, can I find one? Or if it's not unique, can I find any expression for a given point? And sometimes, if we know the equations, we can actually determine the dimension, of course. We can sometimes also determine whether generic identifiability holds. And of course, and then maybe we're really lucky, we can also determine the decomposition from the equations that we find. Okay? So the case of symmetric flattenings or Hankel matrices, this is one example where each one of these can come from the equations. Okay. So maybe not everybody knows a lot about tensors, so here is a slide which explains a lot of different types of tensors with various types of symmetry. Okay? So I say tensor, we're in close to the physics building. The physicists mean something slightly different by a tensor. So think hypermatrix, a Rubik's cube of data. Okay? That's what a tensor is. So the space is A tensor B tensor C, and there could be more than 3 factors. The hypermatrix has 3 indices. It doesn't have any symmetry. Well, we also have homogeneous forms of degree D on some number of variables. We're going to think about the same hypermatrix with D indices, but it has the property that it's symmetric with respect to any permutation of the indices. Well, I actually happen to like partially symmetric tensors, so you can think of this as a system of quadrics, if you like, a linear system of quadrics. And these type of tensors have the property that, well, you're only allowed to permute the last 2 indices, and you have symmetry there. Okay, you could do the same thing with skew symmetry, that if you permute the indices, you replace the entry by the sign of the permutation times that entry, or you can think about partially skew symmetric tensors, and actually the talk here, Abo-Wan hypersurfaces live in this last space. So why all these different types of symmetries? It turns out that in Shmuel Friedland's solution to the set theoretic salmon conjecture, he actually was looking at something here in this space, but he needed something here in this space in order to come up with his equations. So you can't just study one of them. You should study all different types of symmetry classes if you really want to know equations of secant varieties. Okay, so here's just another slide on partially skew symmetric tensors. You write a skew symmetric tensor in coordinates like this, where we just permute the last 2 entries and change the entry by a sign. Okay, so those are the types of tensors. What are the rank 1 tensors in each one of these spaces? So we already talked about the rank 1 tensors in the tensor product, which is the Segre variety, but all of these are classical algebraic varieties studied over 100 years ago, and they have names like that. So Veronese is the space, the variety of dth powers of linear forms written as a tensor. I can just take the same vector and tensor product it with itself d times. The Veronese, okay, the Segre Veronese, we can mix this, and of course this is more general than just two factors, but I just give you one example of things that look like A times B with the tensor product. The Grassmannian parameterizes k-dimensional projective spaces inside of the projectivization of A. And you can represent points on the Grassmannian by a pure wedge product, which is an alternating tensor of rank 1. And then the Segre-Grassmann and is this type, well, I'm going to think about them as systems of skew-symmetric tensors, linear systems of skew-symmetric tensors. In every single one of these cases, if you don't know these varieties very well, you can just think about them as a tensor, a Rubik's cube, such that up to symmetry, all the entries in the tensor are 0 except for one entry, which is a 1. So now you might object, right? A skew-symmetric matrix doesn't have rank 1. But if I ignore the lower half of the matrix, then it just has one non-zero entry. The same is true for every single one of these varieties. Up to symmetry and up to deleting redundant entries in the tensor, there's a single non-zero entry. Okay, so that's what a rank 1 tensor is in each one of the symmetry classes. So how do I email someone the Segre-Grassmann variety? It's a very large variety. I would like to email it to Matt so he can put it into Bertini. Okay, so here's some Macaulay 2 code, just about 8 lines, 10 lines. So how you can email a point on the Segre-Grassmann variety. So I have a little function that defines the rank 1 terms as, well, maybe it's, I don't know if you like to read computer code or if you like to read text. So I need to take something that is rank 1 here and then rank 1 here. So rank 1 things here are just vectors. And then rank 1 things here are wedge products. Well, I can take the maximal minors of a matrix. So in this case, I take the minors of a random matrix and a random vector, and then I flatten the entries of the product of those two things as a list, okay? So this might fail because minors is going to give me an ideal. If I have some repetitions, it'll give me a list that's too short. So in practice, I do something slightly more complicated, but in a sense, this 8 lines of code will give you as many points on the variety as you want, okay? That's good. That's, you know, the Segre-Grassmann variety. If you know all the points on it, well, as many as you want from this code. Okay, so that's how you email the variety to somebody. Okay? How do you email the secant variety? That's this line. You just sum up 5 rank 1 points and you get something of rank 5. Okay. Okay, so now I want to talk about flattening. So we talked about tensors, different symmetry classes of tensors. And the first thing that you should do when you look at a tensor after you ask, rank and so on, well, is it really a matrix? Maybe it's just a matrix hiding. Like maybe all the properties I want to know about my tensor just come from the properties of matrices. So in the applied world, I think they call this matricization of the tensor. They want to take a tensor and write a matrix from that tensor. So I call it flattening. So we're going to take a tensor, and we take this tensor product of vector spaces, we're going to parenthesize like this. Okay? So B tensor C is its own vector space. And A tensor, a vector space, is tensor product of two vector spaces I can think about as a space of matrices. So I can do this in 3 different ways, right? I can pair B and C together, or A and C together, and A and B together. So the tensor product on the level of vector spaces is commutative, so it doesn't really matter as long as I reorder everything all at the same time. Okay, so then let's look at this first one here. I've separated the elements, the first ones, the A's. I put all the constants in this part, and so I have, for each A, I have a different matrix. So if I have, again, my Rubik's cube, I'm taking my cube, and I'm slicing it in one direction, and I'm taking all those slices, and I'm laying them out on the table. And that's a flattening. So here's just one example of a contingency table type thing. they're going to go. Okay. All right, so is it clear where all the indices go? I think it's okay, don't worry. Okay, so let's see. This first matrix, it has, well, 1, 2, 3 in the first entry, 1, 2, 3 in the first entry, and so on. And the second entries, let's see. So the 1s are constant in the third spot, right? And then it just looks like a matrix. And then the second matrix has 2s constant in the third spot. The third matrix has 3s constant in the third spot. So that's how you take a tensor and write a matrix. So what can I know about this? That this matrix has rank at most 3. Right? 3 by 9 matrix has rank at most 3. And so the 3 by 3 minors of this matrix are going to give me some of the equations of the rank 2 tensors. But, okay, well, maybe there are no 5 by 5 minors of this matrix, so that's not really going to tell me anything about the fourth secant variety. So let's see this a little bit more. Why do we get equations from flattenings? So I'm going to realize my tensor now as a matrix, and then by choosing a basis, I can think about this linear map as just stack up all of the slices into a matrix. And what happens in the rank 1 case? Suppose I feed a rank 1 tensor to this linear map. Then, as I told you, a rank 1 tensor has up to symmetry a single non-zero entry. All the rest of the entries are 0, right? So the rank of this matrix is obviously 1. But this construction is linear in the argument, which is this tensor t. It's linear in the tensor if I take psi 0 of t and psi 0 of t prime, and I sum them, I get the sum psi 0 of t plus t prime. Okay, this should be obvious. Right, so I have a construction which is linear in t, and whenever I feed the construction a rank 1 tensor, I get a rank 1 matrix. So matrix rank is subadditive. So subadditivity of rank for matrices says that if the rank of t as a tensor is r, then the rank of this flattening is less than or equal to r. So I want this to be really clear. Flattenings give me a bound on rank. Right, so if this matrix, this flattening matrix, the r plus 1 by r plus 1 minors of this matrix have to vanish if the tensor has rank r. Okay. So, but these flattenings don't get very large. The biggest they can be is the dimension, the minimum of the dimension of each of one of these matrices. So they give us the first equations from flattening. So just so here's one example of a symmetric flattening, or a Hankel matrix, or a catalecticant, as Baron mentioned in his class today. I made these slides before his class, but he mentioned all of these words. Okay, so Macaulay studied this a long time ago, and he showed that the border rank is larger or equal to the symmetric flattenings for any type of symmetric flattening. So what's the idea of a symmetric flattening? Is that you take a degree d form. Well, I think about it as eating d vectors symmetrically and spitting out a number. But if I feed it less vectors, it's going to spit out a form. So I feed s vectors to phi, and it wants to eat d minus s more vectors. This makes my matrix. So feed it s things, spit out d minus s in degree. Okay, so this makes a matrix, and you can compute the matrix in one line in Macaulay 2 by differentiating a vector with respect to a transpose of another vector. It's very easy to put this into Macaulay 2. Okay, so these give some of the equations of secant varieties to Veronese varieties. So what do we know? Some results about flattenings and secant varieties. So a conjecture that sort of encouraged a lot of work in this area is by Garcia, Stillman, and Sturmfels, that said that, well, let me back up for a second. The Segre itself, it's defined by all the 2 by 2 minors of all the flattenings. This was known by Segre himself, I think, over 100 years ago. And in fact, all of those rank 1 spaces just the rank 1 terms are defined by similar kind of equations. This is a theorem, in fact, very general by Costant. Anyway, so Claudiu Raicu proved this Garcia-Stillman and Sternfeld's conjecture that the prime ideal of the secant variety to the Segre product of projective spaces is generated by 3x3 minors of flattenings. That's what Raicu was able to prove. Many people worked on this problem before Raicu proved the strongest version. Landsberg and Manivel, separately Landsberg and Wayman, Jeremita, Catalizano, Gimigliano, many of the Italian school worked on this problem. Allman and Rhodes also worked on this problem for phylogenetics. Claudiu also actually proved stronger version for Segre Veronese varieties, which is... So I want to advertise one piece of work that this variety doesn't really seem toric if you think about it. But if you take an affine open patch on this variety, it's toric. That's a miracle. And that's what the content of this paper is, essentially giving a toric proof of this conjecture that is stronger in one sense, that it works over any characteristic, and it's weaker in another sense, that we only prove the scheme theoretic version and not the ideal theoretic version. So if you're curious about what a secant cumulant is, this is an interesting topic, and I encourage you to check out this paper. I also have a chalk talk on my website next to this paper that you can also look at if you want the short version of the paper. Okay, but flattenings run out really quickly. Here's the first example that I wanted to mention is third secant variety of the Segre product of 3 copies of P2. So all the flattenings are 3×9, and yet I want 4×4 minors. There aren't any 4×4 minors of a 3×9 matrix. So Strawson already recognized what the equations are, and academic brother of mine, Young Ki, proved that Strawson's equations plus their generalizations define all set theoretically all third secant varieties of Segre products. So Strawson's degree 4 equations plus 4×4 minors of larger flattenings do it for any number of products. So secant variety, third secant variety for Segre products, fairly well understood.
So what do you mean by a larger flattening?
So if I have 4 factors, if I have 3×3×3×3 tensor, then I can get a 9×9 matrix. And then I do have 4×4 minors. Here I only have 3×9, so. Okay, so flattenings are great, and they tell me everything I want to know of the cases that are close to being matrices, but what happens after that? How do we find more equations? Okay, one other thing. I mean, if I have the flattening, I can look at its image and its kernel, and it tells me something about the original point that I was looking for here, which is also interesting. Okay, so here is exterior flattenings, and this formulation is due to Ottaviani and further developed by Ottaviani and Landsberg. So an exterior flattening, sometimes called Cazul flattenings, sometimes called Young flattenings, work like this. We recognize that we have a natural inclusion of wedge 2A tensor A star. A lives inside of here. So for me, this is just saying that if I have maybe, I don't know if you study the representation theory here, I'm just saying that I can take one box out of this picture and then I get one box. This is the representation theory version of the statement, but you can, anyway. So because we have this inclusion, well, I'm calling it an inclusion. It's an isomorphism. There's a copy isomorphic inside of there. But I can take my vector space here, and I can lift it to a larger vector space that has a lot of structure, and I can regroup all these terms. So I'm going to take this wedge 2A, move it over to the other side. It hangs out with C, and then this A star together with B. So now I have 4 vector spaces, tensor product together. I'm going to group them in pairs and think about this as a matrix. If I do this, well, and I choose bases appropriately, here's the best example. Dimension A is 3. Then, okay, so I have to dualize this side, put this over here. This is phi sub 1 of T, the first exterior flattening. And this matrix here is a skew-symmetric matrix whose blocks are the slices of the original tensor. So this looks 3×3, but it's 3×3 with large blocks. So now, why do these exterior flattenings give equations for secant varieties. I'm going to repeat the proof that I did for flattenings for exterior flattening. So how did it go? First, the construction is linear in T. So if I take this argument T, and I take another tensor T prime, and I form this 3 by 3 matrix of blocks, and I sum those two matrices, I get the same thing as if I had started with the sum of the two tensors. So it's linear in T. Then the base case is what changes here. If I feed this matrix a rank 1 tensor, remember, a rank 1 tensor has a single non-zero entry up to symmetry, and all of the stuff that I'm doing respects the symmetry. Then I notice that, well, my single non-zero entry is right here in T1. And it's also up here. And they're in different rows and columns. So this matrix has rank 2 when T has rank 1. All right? So subadditivity of rank implies that if I have a rank R tensor, then the exterior flattening, this phi1 sub T, has rank less than or equal to 2R.
I have a question.
Yes?
Are we assuming that B and C have the same dimension?
So this it doesn't matter if they're the same.
This matrix is not skew symmetric.
Well, it's block skew symmetric, and it's not skew symmetric at all, even if, right? Because this is not T3 transpose. It's only symmetric. It's only skew symmetric when we're doing a exterior flattening of a partially symmetric tensor or a symmetric tensor. That's coming. Okay. So, well, if this matrix has rank 2R or less, then the 2R plus 1 by 2R plus 1 minors are necessary conditions for the border rank to be less than or equal to R. So the art here is to find a type of a linear map that doesn't grow too large in rank when you feed it a rank 1 tensor, but is a big matrix, so it has more room than the flattenings had. So there's a little bit of art to this, figuring out what is a good exterior flattening. So just here's the same thing I was saying here. Here's my single non-zero entry. Here's the other one. This matrix obviously has rank 2, right? Okay. And here's the construction is linear in T. So I'd sum these two guys to get this matrix. That's the same as this exterior flattening. Okay, but here's the case for the partially symmetric case that Bernd was asking about. So let's suppose that instead of B and C, I have B, and I also consider the symmetric matrices Sym2B. Well, these partially symmetric tensors then can be split up in the same way, but since these blocks, T1, T2, and T3 are symmetric, this matrix ends up being skew symmetric, so therefore its rank is even, and all the same construction works. Well, now I have, instead of minors, I have Pfaffians, and 2 times R plus 1 by 2 times R plus 1 Pfaffians are necessary conditions. So the interesting thing to me here is that we symmetrized the construction and the degree of the equations dropped, which is, I think that's really, I like to understand more when this sort of thing happens. Okay. So if you don't know what a Pfaffian is, this is something we can talk about afterwards. I hope that you know what they are, but if not, I'm happy to share afterwards. Okay. And here is, if you wanted to know what other exterior flattenings look like, if this A has dimension 4, for instance, then I don't know if these matrices look familiar to any of you that study commutative algebra, but these are the Koszul matrices that show up in the resolution of the maximal ideal. And we tensor those Koszul matrices with our tensor, and here's just a sub-block that was the one we looked at before. Well, that's how you construct more general exterior flattenings. Okay, so subspace varieties. So we talked about flattenings, exterior flattenings. Now let's talk about subspace varieties. So subspace varieties, the very first kind are, okay, so this is a sub PQR of A tensor B tensor C. There's a variety of tensors such that there exist subspaces in each direction, and the tensor lives in this smaller tensor product. Okay, so for matrices, this is equivalent to lower rank matrices. I'm going to think about my Rubik's Cube having only non-zero entries in an smaller upper triangle, upper corner block of the matrix. So that would be a type of subspace variety. So those tensors that after symmetry, you can move them into a certain block. So Landsberg and Wayman proved that this variety is normal with rational singularities. That should sound like Wayman-Kemp desingularization. That's what they used. And they proved that the ideal is generated by the minors of flattenings of the different sizes. Okay, so subspace varieties are exactly the varieties which are defined by the minors. And the subspace varieties also contain secant varieties. So this should be, if I have only R sum n's for a general point, then I can just take each of the terms as being the bases for a vector space in each direction, and that'll give me something on the subspace variety. So the subspace varieties give me some of the equations of the secant varieties when they're not. Okay, so if they're not the whole space, then this is a good place. So I already mentioned Claudiu-Raicu's result. So we also have partially symmetric analogs of subspace varieties. So this subspace variety, sub PQ of A tensor Sim2B, is a variety of tensors such that there exist subspaces in each one of the vector spaces, A and B, and T lives in this smaller tensor space. So with Dustin Cartwright and Dan Ehrman, we showed that this variety is defined by minors of the usual flattening and minors of this other flattening. Okay, so these minors give some equations for secant varieties of partially symmetric tensors. And the other thing we were able to show is that when the rank is less than or equal to 5, this type of partially symmetric secant variety, its ideal is generated by minors of flattenings and Pfaffians of exterior flattenings. Okay, so just exactly the construction which I showed you before, and we needed a bit of commutative algebra to show that these were all of the equations. For r equals 6, we don't know the answer, and for r equals 7, these are not enough equations. Okay. Okay, what about skew-symmetric subspace varieties? So this subspace variety of alternating forms, so we can think about this as alternating forms that only need p variables to express. And, well, the equations of this variety are really mysterious. So if k equals 2, we're talking about skew-symmetric matrices, and we understand the conditions for a skew-symmetric matrix to have smaller rank. But when k is larger than 2 and the dimensions work out so it's still not matrices, we have some extra symmetry, then Ada, Borelevi, and I showed that the ideal of this subspace variety, this is the first non-trivial case that wasn't already done by Wayman and his student, Olga Porras. This variety in the 35-dimensional ambient space or a 34-dimensional projective space is ideal, is generated in degree 3 by two types of cubics, 28 in one case and 224 in another case.
Luke, how does this relate to the secant variety of this Grassmannian?
So this contains the secant variety of the Grassmannian, and the equations for secant line variety, I think, are these. Yeah, yeah. So these are, yeah. So the point here is that the equations for subspace varieties are not always just minors of flattenings. It's not obvious how to always find them. We had to work pretty hard with geometric techniques, some spectral sequence ideas in order to figure out that these were the correct equations. Okay, well, what's the general story? So Ottaviani united a lot of different sources of equations for secant varieties in one single construction, which I've been telling you, exterior flattenings. Some of this has been around for a very, very long time. So Arn holds degree 4 invariant for the space of Fermat cubics. It's Zariski closure. Well, you can express that equation as a symmetrization of an exterior flattening. Toeplitz also understood this one case of this hypersurface in P29, and Ottaviani expressed this equation as an exterior flattening, and I already mentioned the work with Dan and Dustin that handled smaller secant varieties inside of this one. And then also we generalized to not just P3, but Pn in the second case. Partially skew-symmetric varieties, which is really supposed to be the topic of this talk, were studied by Hiratachi Abo and his student Wan, and they wanted to understand dimensions of these varieties. And they had a list. Here's one of the families which they proved were defective. We expect them to fill this ambient space, but they miss by just one. So there are hypersurfaces. I'll come back to this in a second. Strasson's equation, Ottaviani showed that you can express this as an exterior flattening, and many more cases in this paper of Landsberg and Ottaviani. So I was hanging out in Berkeley, and it happened to be that John Hauenstein and his student, Noah DeLeo, were there, and they said, we're looking for interesting cases of hypersurfaces that people don't know the equations for. Do you have any examples? And I said, well, I have a lot of examples. Abo-Wan hypersurfaces, for one. So I already told you in the very beginning of the talk how to email an Abo-Wan hypersurface to somebody, and I emailed them these hypersurfaces, and I'll tell you in a moment how they found the equations, but here's on one page a very large polynomial, okay? So here's this fifth secant variety of this partially skew-symmetric space of tensors, and well, we can do this exterior flattening again, now paying attention to the skew symmetry. And you can write down the matrix that represents this linear map as a Kronecker product of two skew symmetric matrices. So, okay. Well, this is the result of that. It's a very large matrix. It doesn't fit on my slide. But this block of zeros is just this 0 times this whole matrix. Right, so the Kronecker product is replace this matrix in every entry here. Take that scalar times this whole matrix and increase the matrix by blocks. Okay. So the same exact proof as I mentioned before. This matrix, which in this case is 21 by 21, if I feed it a rank 1 tensor, it actually has rank 4. Okay. So the rank of this matrix is less than or equal to 4R, if R is the rank of my tensor. So if T has rank 5, the rank of this matrix is less than or equal to 20. So the determinant of this Kronecker product of matrices is 0. And so we can check also that that determinant is not trivial. It might be trivial, right? The determinant of a 3 by 3 skew-symmetric matrix is always 0, no matter which matrix. So we might have gotten unlucky and found the 0 equation, but we can check that random tensors have rank 21 for this construction. This construction has rank 21, so the determinant's not trivial. And we verified this in Macaulay 2, like this. Okay, so declare my ring, declare my two matrices, take their outer product, and then just print out all of the ranks, and the ranks go up by 4, and then the last case, full rank. If you want to write down this polynomial, declare another ring with x, I, j, k as the variables, and then write down this form, which has v's, w's, and x's, and just differentiate this form against this matrix, and you'll get the matrix that we're actually interested in. This is my trick for telling Macaulay 2 a tensor. I just use different named variables, and I don't have to write the tensor symbol. I just can multiply them. Okay, and then this, I don't recommend doing this on your laptop. Okay, so this last, take the determinant of this 21 by 21 matrix. It may or may not complete on your laptop. Okay, so that's the matrix, and its determinant is the equation of that hypersurface. Well, wait a minute. It's only one equation of the hypersurface. We don't know if that polynomial is irreducible or not. That was Baron told us yesterday. Every time you meet a polynomial, ask it if it's irreducible. So how do we prove that? So here, this is the Bertini team comes to the rescue. So after I emailed them the Abo-Wan hypersurface, this one, computation in Bertini says that this hypersurface has degree 21. And I put a star on here because this is true with as much accuracy as you care to ask the computer. Okay? So it's true. Okay? But it says, so this computation says the hypersurface I emailed them is an irreducible hypersurface of degree 21, and it happens to live inside of the 0 locus of a degree 21 polynomial. So therefore that polynomial is irreducible. Okay, great. So we proved a theorem. That determinant is irreducible. Great. So, well, let's not stop there. That wasn't too hard of a computation. The next one, the 8th secant variety for this next case where we have Grassmannian or projective.
So Luke,
Yes?
we couldn't do this symbolically? I mean, for example, by specializing to the plane?
So I want to say that the one theme of my talk is this is a proof of concept that these techniques work. There are other methods for, and yes, if we have a polynomial, if we could write it out enough terms to prove that it were irreducible, yes. We still have a conjecture that all of the family of these determinants are irreducible, but I haven't tried to do the method you suggest.
So one thing is, in theory, but not practice, because software is not there yet, these stars can be removed because there are
So actually, all of these stars are removed in this case, in the ones that we're talking about. And since we could use your software to.
But the irreducibility, that's not been implemented very well yet. The homotopy tracking.
I see.
By tracking. That certainly the solutions can be verified, but the tracking is not there yet.
So there are other ways that we can prove this is the right equation, but this is proof of concept, okay? We wanted to check whether Bertini could find the degree of very large hypersurface, and yes, it can. In this case, 63 variables. Here, how about this one? 165 variables. Found a degree 33 hypersurface, and it turns out that the exterior flattening has degree 33.
Yeah, well, one thing, the calculation is just on a line to find the degree of hypersurface.
Okay,
so
that's coming in the talk.
It doesn't matter.
That's coming in the talk. It's next slide. Okay, but what about this one? It has degree 6. This was a huge surprise. We have this really large hypersurface and 60 variables. Surprise, it has degree 6. But we don't have any 6 by 6 flattenings, and we don't have any 6 by 6 exterior flattenings. So what do we do if we have no other choice? We don't know how to find the equation of this hypersurface, some degree 6 hypersurface. So I have 60 variables. I wonder if I can just compute, are there any linear forms in the ideal? Are there any quadratic forms in the ideal? Any cubic forms in the ideal? And this is what the Hilbert function of the coordinate ring and the ideal should look like if what they said is true. And over here we notice that there are 82 million, am I counting right? 82,500,000 some monomials in degree 6 on 60 variables. So what you could do to find this equation is just compute the kernel of a matrix constructed by listing all the variables as the rows and listing that many points as columns, and maybe you should do a lot more points in case they collide. Compute the kernel of an 82 million by 82 million matrix. So I don't recommend trying that. Even the experts in linear algebra don't use matrices that big. But that's in principle what you could do. Or you could feed 82 million monomials enough points until you found the coefficients of your polynomial. Okay. Right. Well, at least in the first case, we can find that it's not linearly degenerate. Like I verified this in Macaulay 2 is easy. But that's not an easy computation. So what we've been doing the whole time is we haven't mentioned symmetry almost at all. So let's talk about symmetry. So the symmetry group of this variety is GLA cross GLB. So GL3 cross GL6. This is a big group acting on a 60-dimensional space. And we shouldn't just ignore this symmetry. We should treat this problem with respect to the symmetry that's there. So here's a little bit of representation theory, classical representation theory. It says that, well, first of all, I can decompose my coordinate ring degree by degree because I have a homogeneous, I have a projective variety. Well, the C star action imposes this decomposition. But when I have a larger group, it induces a finer decomposition of the coordinate ring into modules which are indexed by partitions. I'm sorry this is a little bit small, but the way you want to think about this is that it cuts up the degree d space of polynomials into many pieces. So I have Schur modules, and I can compute the multiplicity of each one of these Schur modules by some character theory, which is best implemented in a program called Lie. It's also in Maple. Okay, so that's how the coordinate ring splits up, and so I can split up this 82 million by 82 million matrix into blocks and try to solve each one of these blocks. Actually though, I should do one more thing. Use Lie and ask, what does this decomposition look like? So in one line in this program, Lie, you can find that decomposition of the coordinate ring in degree 6. And it says that there's only one SL3 cross SL6 invariant of degree 6 in this coordinate ring. So I have an invariant hypersurface, and I know that there's one equation in degree 6 that's invariant. So I'm done. But I would like to tell you what that equation is, instead of just saying, well, it's the unique invariant. So here's how you construct that invariant. So these two partitions, 2, 2, 2, that's a partition of 6, and 3, 3, 3, 3, this is a partition of 18. I need to give you a recipe by Young symmetrizers to compute this polynomial. So here's what I do. This is the fillings after a brute force search that work for this algorithm.
So these are not trivial. They're the tensor part of the determinant, aren't they?
So the scalar trivial. What I mean by scalar is yes, exactly. So the one-dimensional representations.
The determinant representation.
Yes.
Determinant is 1 in SL.
So I said SL invariance, but I actually care about GL. So that's why I'm not just putting C here. Okay. So I really care about the twist by the determinant, and that matters.
You'll want that extra information.
Yeah, exactly. So here's how the algorithm works. So I couldn't figure out how to use the Young Tableau package to put colors here. So hopefully you can see A, here's the column. A, B, D are the names of the columns, or the rows of this matrix, right? And then they get an extra character. They get a 1, a 2, and a 3 as they go across. So for the first column, I make a 3 by 3 determinant. For the second column, I make another 3 by 3 determinant with those letters with extra decoration. Okay, do the same thing for this filling. So I have A, B, C, C. So A's with 1s, A's with 2s, A's with 3s, A's with 4s. Okay, so, and then going across, here's my B's, here's my C's, and another C. And I do that for each column. And I keep track of how many A's I've used, how many B's I've used, and so on. So things are really small. Small matrices are so hard to see, but it wouldn't fit on the slide otherwise. So, okay, so I have a product of 2 3 by 3 determinants and a product of 3 6 by 6 determinants. And I multiply them in Maple so that it holds them as a product instead of multiplying them in Macaulay 2 and getting a billion terms, okay? And then I want to extract in this polynomial, each time I see an A with an I with a single index, and then 3 more A's with double indices, keeping track of the skew symmetry, I'm going to replace that monomial with a single variable. And then I'm going to run over all the monomials in the polynomial and then replace each monomial with variables like this. Well, they're not exactly monomials unless you think about them skew symmetrically. So I just keep repeating this for each letter, keep peeling off the different terms and then replacing them with variables, and then eventually I get my polynomial. So this is possible to do. This finishes in Maple. And here's our theorem. It says that the hypersurface is defined by the image of this map, which I just described to you. The resulting polynomial has 10,080 monomials, 5,040. 7 factorial of them have coefficient +1, and 7 factorial of them have coefficient -1. So maybe we already knew this polynomial for a different reason. It seems really coincidental that those would be the cases, but this is the brute force proof of concept way to solve this problem. And also, I didn't put a star in this theorem. So we used Bertini to find the degree, and then we used representation theory to find the equation. We could say, well, maybe the Bertini computation missed a point or did something, maybe there's a path tracking that went bad, but we can remove the star because there's no lower degree invariant. There are no other possibilities other than this polynomial.
So this, with hindsight, the 10,080, could we have guessed that by looking at torus invariant monomials? You could have solved your linear algebra problem and gone to 10,000 by 10,000 make found the +1 -1 solution. Also,
Yeah.
or are there many more torus in there?
I haven't checked that. I think you, yeah. I think you have to count how many fillings of a different type, not the kind that I put on here. You have to count the number of fillings. Those are the type of monomials that you would want to consider. So all fillings that use 3 letters with repetitions and 3 letters with repetitions here, and maybe that number is this, but I don't know.
Yeah, well, 7 factorial is rather interesting.
Okay, so proof of concept. The representation theory, classical representation theory, Hermann Weyl a long time ago, that stuff works to find the equation of this hypersurface. So I'm almost done. We wanted to know if there was an Ottaviani type expression. So why not an exterior flattening? And we did this, but it turns out that this exterior flattening actually factors through a smaller map, so its rank is smaller than expected. There's a very large kernel for this exterior flattening, so it can't actually detect the rank. So what we're hoping is that 6 is like the cube root, this degree 6 equation is a cube root of some degree 18, which would have been this one, some 18 by 18 minor, this matrix, but that's not the case here. And we don't know if there's a linear algebra method, just like rank of matrix method to do this. Okay, so here's what Bertini does, and then I'll finish. I'm sorry to go right up until 6, but so here's what you do. You have an irreducible hypersurface and pick a line so that the degree of the hypersurface intersect the line is, well, the degree is equal to the number of points in the intersection of the hypersurface and the line. And then we just pick a random point from the code that I emailed to John and Noah in the very beginning of the talk. We can generate as many points as we want in this intersection. Okay. And then start our loop. So now we perform something called monodromy to these points in W. And we move them around and we see if they're all on the same hypersurface, essentially. So maybe I'm not an expert in Bertini, and if you want to know more details, you can ask.
This is going to generate points that are on the same component as the point you started with.
That's right. So I want to keep doing this until the test verifies that I have all the points that I'm looking for. Okay, so these are the results of the Bertini computations and how long they took, just in case you're wondering how hard these computations were. So this hypersurface has degree 6, and it took only 6 monodromy loops, 50 seconds on a single core. Okay, not too bad.
You can do that on your laptop.
Yeah. Well, you can do that on your laptop if you know how to ask Bertini how to do the computation. Okay?
That's the thing.
Okay. So, and that's up to numerical accuracy. Then this hypersurface is degree 21, the other one has degree 33. In each case, it took not too many loops, but 16 2.3 gigahertz cores, 2.5 hours, 2.5 minutes, and then 32 minutes for the other one. So still not too bad for computations.
Put it on your laptop overnight. When you're traveling, sometimes you have to do that.
Yeah. I would probably just log into a server and let the server do it. Okay, that's all for my talk today. Thank you very much.